Yeah, now it's picking up. Okay. Now it's picking up. Okay.
You want to do not do an introduction one more time? Okay, great. This is going to be joint work with Cassandra Marcuson, who's a graduate student at Harvard with me, and Ronit Rubinfeld.
Sorry, I still don't see the things. I don't know what happened. You don't see? Hello. Okay. I don't know why I don't see any.
So there is a green bar that goes up.
Yeah, it'll show up when.
But there's something up.
Where is something else?
No, there's this microphone.
That is okay.
No, that isn't before.
Anyway, those who are on Zoom, right, they should have been here.
They're not hearing you say that.
Also not just recorded, right?
All right. So, oops. Okay. So, the motivation for this work, this is really a new model of, a new class of algorithmic problems that we are considering. And the motivation was that, there are lots of these algorithms that we develop for randomized, distributional inputs. So random graphs, X, Y, Z, and so on. And then you then run it on a particular instance and you don't really know whether that instance came from that distribution. So in the past, people have tried to address this question by looking at various aspects. They try to say, is the distribution really right? And you test whether the distribution, but on a single sample, you can't really do that. So you really have to do something on this particular input. Can I trust this algorithm or not? For this, we are proposing a new model of, a new class of questions or new way to define the correctness of algorithms. And then in this model, we'll try to come up with some things showing that, look, if you work within this model, there are some good efficiency advantages. Okay. So, and the rules that we will follow are sort of, where is this phrase quality control coming from? It's from, production lines or some such thing. Imagine like a whole series of products are coming out of this line. You expect most of them to be good. So what do you usually set your standards as? You do want to make sure that if you are, if a product is actually bad, it is rejected. Okay, it would be sort of bad for you and your reputation if bad products are being sold in your name. Good products, on the other hand, you don't need them to be always accepted. If it's going to be helpful in your efficiency consideration, you're quickly looking at this product and saying yes or no, there's no reason why you should accept all good products. But of course, you would like to make, you don't want a quality control manager who sits at the end of a production line and says every product is bad. As long as they're saying most good products are good, you're very happy with it. And that's exactly the kind of metric or kind of objectives that we'll try to axiomatize into definitions of algorithms, or that will formalize into definitions of algorithms. So these are going to be the parameters of quality control problems. So a problem is going to be specified by a function that you want to compute, or a parameter. In our case, we want to know this parameter. If it's close to 1, that means the product is good. If it's far from 1, then this is not the right product. And a distribution on inputs. Okay, so both of these are going to be part of the things. And you ask the question, have I managed to solve rho on distribution D or not? If you've solved it on distribution D, doesn't mean you solved it on distribution D prime. Doesn't mean you've solved rho prime on distribution D. Okay, so every pair defines the name of a thing. And this parameter that we are thinking of is really going to be a real valued parameter. In fact, let's think of it as a positive real valued parameter. But really, we think of it, this parameter, if it's close to 1, it's very good. If it's far from 1, the product is bad. We want it rejected. And so and then there's a distribution on all possible inputs. The algorithm solves this problem if the probability that you're accepting this an input is close to 1 on inputs drawn from this distribution. Okay, so this kind of a notion will make sense only if rho of x is usually equal to 1 on x sample from this distribution. We could have defined this thing differently for other categories, but for the time being, we want to think of decision problems. And here it makes a lot of sense to say when things are chosen from the right distribution, the product should be good. So rho of x is going to be usually 1. And the algorithm should also be usually saying 1 when the input is drawn from the distribution. On the other hand, if you happen to have an input, doesn't matter where that input is coming from, for all x, if rho of x is far from 1, then you must reject with high probability. And this high probability is over the internal random coins of A. It's not over anything related with x. Okay, does this make sense? Yeah.
How is this different from setup in which you have this random sat instance?
Exactly. So great question. So okay, the question that we're going to ask is whether this thing. I forgot to add a few slides on. Meant to add a few slides on related work. Let me do that now. Oops. God. This thing's got a. Sorry. Let me try doing this. So there is, in general, this kind of a notion has sat around in average case complexity. My pen is probably also flaking out on me. So is that? No, it doesn't look
I
bad.
think it's in some dotted line mode or something.
Is it? No, I think it's, yeah, it's just, no, it's the pen, let's say. Okay. In average case complexity, you often have the same two features describing a problem function statement that you want to compute and a distribution. And let's start with the most traditional definitions, AK11 and so on. There are two notions that actually have existed in the literature of what it means for a problem to be solved on a distribution. One says you always solve the problem right, but your running time is small on most inputs drawn from the distribution. Okay, this is a pretty safe definition. So if your algorithm runs and produces an answer and so on, but in this notion, this is kind of a little too aggressive. People often end up not finding algorithms because there's a tiny probability of inputs on which the runtime is too high or things like that. So you just somehow it's a strong notion of working correctly on average, but it's somehow not as nicely composable as we'll see in the current setting. A second notion in average case complexity is that you're usually right with high probability. Now, our notion actually sort of strictly sits in between the two. It sort of says that if you have an algorithm which is always correct and sometimes runs slowly, then you're going to satisfy our completeness and soundness. If you're going to have an algorithm which, so this algorithm will always compute the parameter and then you can decide whether it's equal to 1 or not. Now, if on the other hand, if the algorithm, if you have a quality controlled algorithm for rho and d, you can just it satisfies the definition of an algorithm. Whenever this algorithm rejects, you just sort of output a 0 value or something, and this will be a safe algorithm according to the other notion of average case complexity. So this is somewhere in between. And when do you, sorry.
So, like, is that like is closer to the random stat kind of situation where either you're always satisfiable with high probability or
good. So that's the good thing. So I think let me bring up this thing, Feige's definition of resolution complexity. So there are two classes of questions that we've considered in average case complexity, which are very common. Many of them are kind of these NP problems. I produce a random sat instance with very low density. And then I ask you to find a satisfying assignment. A satisfying assignment exists with high probability. I ask you to find a satisfying assignment. You can just ask the question, is it satisfiable or not? And you are safe with respect to satisfiability. So when you say it's satisfiable, it is satisfiable. You found a satisfying assignment. When you don't find it, you just give up and you say it's probably not satisfiable. Okay. So that in that definition, you're satisfying some sort of a quality control. You're solving some quality control problem very naturally. And so in that setting, certainly we've seen these kinds of definitions implicitly considered in the past. One case where we actually applied it to a co-NP problem made it even more interesting. And here Feige was actually trying to determine how do you prove that a formula is not satisfiable? And non-proofs of non-satisfiability in principle could be exponentially large, but you want to say on random, it's should be, on random instances, it may be short. So now you consider a SAT formula which has, root and clauses per variable, so density of root and per variable or some such thing. Huge number of clauses, very, very likely it's going to be unsatisfiable. How do you prove it? And he said, well, an algorithm which works in this quality control definitions would be considered a proof of unsatisfiability. And that's exactly how we want to use it in today's lecture. The main difference between what we are going to do today and the kinds of problems that we're going to look at today and these problems that have been considered in the past is we are considering the sublinear time context, and there things look very different. Okay. So,
Can we look that once?
sure. Yeah. Previous slide.
Just the definite, yeah. So here you're drawing one sample from distribution B, that's X.
Yeah.
Its evaluation is rho of X.
Yeah.
And your algorithm wants to compute rho of X.
It's asking the question, is rho of X roughly 1 or not?
So can you think of it as like property testing for properties that are almost always satisfied?
You could also think of it that way. There is an interesting thing. So let me make one contrast with respect to property testing in particular. So actually, let me get to that in a minute. Okay. So what kinds of problems are we going to consider today? We want to consider problems that are not NP problems. Co-NP would be nice, but morely, so we're not really going to look at sharp P problems, but let's think of it as fixed parameter sharp P. Okay. Or what's the concrete problem that we can think about? Count the number of K cliques in a graph, where K is some very large constant. Okay, so we do care about how the running time depends on K, but you should also think about if there are sort of leading constants which depend on K, we don't care what they are. Okay, so exponents depending on K, we will care about. So some large constant K. Now we're going to pick random graphs where there are n vertices and p edges, and the probability that any one pair of vertices is connected is p. P and n are related to each other in our examples, and so p is going to be some function of n. Think of it as p is going to zero very fast, and n is going to infinity much, much, much faster. Okay, so those are the settings that we are looking at, and now we are asking the question: can you count if can you think? You're looking at an input graph, saying, is this really from GNP with respect to the parameter, which is the number of K cliques? Is this really looking like the number of K cliques in GNP? Does it have that number? Okay, so in this setting, an average case weak definition algorithm would always say yes, because this says, is the number of cliques looking like GNP? On GNP, the answer will be correct if you just say yes, the number of K cliques is whatever it is in GNP. We don't want to do that. We want to do this somewhat differently. For the sake of formality, let me just define some notation, but I'm really not too worried about, we won't necessarily work with this notation too heavily, but we should have a parameter. That parameter is going to be what I call rho sub k. Rho sub k is just the number of cliques that I see in this given graph divided by the expected number of cliques in a random graph of this size. Okay, so I think, sorry, in this case, I'm calling it mu sub k. Later, I thought let's change mu sub k to be the probability that a random k set is a clique. So maybe this should have been mu sub k times, well, never mind. So I don't know if this notation is going to be consistent in the talk. So, but the quantity that I want to look at should be something that's roughly 1 on random graphs. Okay, so the number of K cliques in this graph divided by the expected number of K cliques in a random graph. Okay. And so this is the problem that I want to look at. And the kinds of things that I want to, the algorithms that we want to get are things whose running time depends on P and K, but not on N at all. Okay, so the number of vertices, I don't want to have any dependency. So as long as the number of vertices is large enough, I should be able to get this thing. But the runtime that I'm aiming for is something that looks like 1 over P to the order of K. Yeah. So does that make sense?
What did you say about P and P is going to 0 or
K, think of it as 100.
K is 100?
Okay, P is going to 0. Okay, and once P is being set, N is going to go to infinity.
N is going faster.
N is going faster. you want n to be large enough that the number of k cliques is concentrated. It will be concentrated if p is like n to the 1 over k or something like that. Okay, 1 over n to the 1 over k, but let's not worry about it. So p is like log n over n, think of every edge will be present with probability 1 over log n.
Okay.
It's good enough for us to think about it. In that kind of a setting, this is like a polylog n time algorithm. And it works in, so of course, because I've made p a fixed function of n, there's dependence in the runtime on n, but it's really just a dependence on p. It's 1 over p to the order of k, and this is the kind of right dependence that you should have. And then we have some extensions which says, if instead of counting the number of k cliques, I want to count the number of induced copies of some finite size graph H, like a 4 cycle or a path of length 10 or things like that, we can get bounds for all of these. In each case, we get an exact exponent on 1 over p, and that exact exponent is exactly the maximum degree in this graph. Okay, so this is thing, yeah.
When you say solved, what is it?
So good. So it means that there is an algorithm which will solve this problem in this much time. Since it solves it in that much time, it's also, this is the query complexity of the algorithm. How often do you ask the question about the graph? And what kind of access do you have to the graph? Adjacency matrix. You can ask for any pair of vertices u and v, is there an edge between u and v in this graph? Okay, does that make sense?
So naive algorithm will just look at all possible cliques, just count. And
Yeah, so
the correct answer.
Good, yeah.
Compared to that, you want to do this in Sublinear.
Exactly. So the naive, great question. Thanks. So the naive algorithm would be look at all the, so go through the graph. There are n square queries, and then there'll be n to the k possible subsets of vertices that you want to look at and see if it's a clique. And so query complexity will be n squared, running time will be n to the k. We definitely want to beat it. Now, there is a less naive algorithm, which is designed to be sublinear, and we'll try to talk a little bit about that. But there was a question about sublinearity at some point.
Madhu, can you
Yeah.
also sample and just check? I mean, like, so I'm assuming that P, etc. is fixed. So I know what the right number of k cliques is supposed to be.
Right.
And can I just sample what sets of k vertices?
Absolutely.
Okay.
Yeah, and I'll get to it in a
Okay.
minute. Okay. So just a quick note. So there is this contrast with sublinear time algorithms that I want to draw. One thing is we are not going to solve the problem on worst case, whereas sublinear algorithms really do solve the problem correctly, some problem correctly on every input x. Okay. For that input, no matter how maliciously it's contrived, etc., it will solve the problem correctly. In our case, we are saying, look, if this input happens to have the right number of k cliques, we might say yes, we might also say no. I mean, I'm allowed to say in a graph which has the right number of k cliques, the answer is no. It does not come from the right distribution. Why? Because that's my completeness condition. On inputs drawn from the right distribution, I'm allowed to say no, as long as I say that with very tiny probability. Now, the other thing is, in contrast to sublinear algorithms, where the most natural measure of correctness of an algorithm is, if I say something is true about x, it may not be true about x, but it is true about some tiny perturbation of x. So I can change. So given a graph, does it have the following coloring number? Well, maybe not, but if you change this much fraction of the edges, the coloring number would be that. Okay. We are not allowing ourselves changes on the input side. We are insisting that the parameter be approximated. The parameter should capture whatever approximation you want to do. If you want to put in some distance to add a 3-colorable graph as your parameter, then put it into your parameter. Don't don't call it the definition of the problem, solve 3-coloring or whatever. Okay, so in that sense, we're just saying, look, we'll go directly for the approximations, and this makes a difference. When you're looking at a graph and counting the number of k cliques, you may be able to put in a clique of size square root of n in there somewhere inside this graph. And then suddenly you've created a huge number of k cliques. Oops. That certainly should take care of the pen. Still works. Maybe didn't. All right. So now so these are the results. And I think we are ready for the naive algorithm that I thought of less naive than the one that you indicated, but yeah, that would have been the algorithm number 1 is, or 0 would be probably do it in non-sublinear time. The first sublinear time algorithm would be what Ramprasad suggested. Pick a random subset of vertices, check to see if it's a clique. Of k vertices, check to see if it's a clique, repeat. Keep repeating this experiment and now ask the question, what fraction of vertices are forming a k clique? So let's look at what's the running time of this algorithm. So sorry, from now on, mu sub k should really be this p to the k choose 2. This is the probability with which a random subset of k vertices should form a k clique in GNP. Okay, so keep picking sets of vertices and then ask the question, is it a k clique? Is it a k clique? Is it a k clique? And eventually draw enough samples that you can estimate the fraction of k cliques in the graph. This would run in time roughly inverse in that number, and that's like 1 over p to the theta of k squared. Okay, so this is the naive algorithm. This is the one that we want to beat, and we are eventually promising that we're going to beat it by rather than k squared, we'll have k in the exponent. Okay. Now, I want to say one thing about this thing. This intuition, which is kind of very naive, saying, look, sampling. So we're looking at for some event that's going to happen with probability p to the k squared. We should, it makes sense that in order to get the event to happen, we would have to run so often, 1 over p squared times. That intuition turns out to be wrong. There's another intuition coming from sublinear algorithm saying this is the right number. And that is a proven lower bound saying, if you want to count the number of k cliques in a graph and want to verify that it's really like this, the probability of a random subset of k vertices being a k clique in this graph is roughly that number, then you have to actually run in this much time. That's a formal proven lower bound in the worst case complexity. So in this case, worst case complexity is really looking like this. So the model has made it, will make a difference, that's the promise. Okay, that's okay. So here's a less naive algorithm, and actually let me already highlight what I know about this, which is I don't know actually if this algorithm works or not. This is what you might try next, and strangely enough, we haven't been able to analyze it yet. So we'll go to some slight variant of this algorithm, but this is what we're going to do.
Go back to the naive algorithm.
Yes.
So how does the model get around the lower bound? It's because
So you'll see one thing that you will see firstly is that, just to find a k clique, you don't have to make, you don't really have to make 1 over p to the k squared queries. Okay. This is how you might go about trying to find a k clique. It's not provably correct, but this is, the intuition is completely here. Pick a set of size 1 over p to the theta of k, a random subset of vertices of that size. Look at the induced subgraph on this. How many queries? 1 over p to the theta of k still. Now, does this graph have a k clique? And the answer is that, in GNP, you should have found a k clique by now. In fact, if you're doing it enough, if there's enough bloat between this number and, the theta of k, etc., you'll find you should have in GNP, you should really have a good estimate of the number of k cliques or some such thing. Yeah, but of course, it doesn't make any sense to ask the question, how many k cliques are there in GNP? So you don't have to look at the graph to answer that question.
Well, I think as a result of Bogdanov and Tradusan, at least in the property testing model, so the worst case of inputs, and in the adjacency matrix with their input, then to check something, you just pick a random subset of vertices and check if the induced property is true, or which is basically what the naive algorithm. Isn't there a
right? Great. So there is this thing called a canonical tester for graph properties, especially, which is saying if you want to test for some property in a graph, then you might as well pick a random subset of vertices, look at the induced graph, and ask the question if if something, and actually one thing that they do even there, I think, maybe Bogdanov Trevisan, maybe Goldratt Trevisan, I don't remember, but even there, I think they do something like this, that the property that you may test on the induced subgraph may be different than the property that you were starting with.
Yeah,
So
because it should have some hierarchical features and some.
something exactly. And you will also see something like that emerging in our case. But all I can say about this is, so what, it's clear that, GNP will pass this test with high probability. You pick this thing. So completeness is fine. It's the soundness that we are worried about. I pick an arbitrary graph with this thing. We've tried the most natural strategies that you can try in terms of GNP, in terms of worst case graphs. Nothing really seems to foil this algorithm, but we have not been able to analyze it. Okay. Why have we not been able to analyze it? One of the big challenges is to try to understand what's the variance of the number of cliques that you would try to see over here. Variance is a little unintuitive to look at, but let me give you a sort of a quick idea of where the variance comes from. Something that's kind of closer and something that we might be following in future, in the rest of this talk, is this McDermott's bounded difference concentration theorem or some such thing. Says if I'm looking at some function on S variables, so from now on, the following is the variant of the algorithm that we'll be thinking of. I'll pick S vertices from this graph independently. Okay, each vertex is sampled from this graph, and then with replacement, I sample a new vertex. So maybe I'll sample the same vertex twice, etc. Whatever it is, I create a copy of this vertex, and then I put an edge between two vertices if the vertices that I had sampled had an edge between them. I've got a graph. On this graph, let's count the number of k-cliques. Okay, and morally, you should really think of it as sampled as vertices. What happens? A key factor that determines how good the concentration results work over here, the number of k-cliques that you expect to see, etc., the expected number of k-cliques will be very directly proportional to the number of k-cliques in the original graph. If the original graph, this is all independent of the underlying distribution from which the graph is chosen. From now on, the graph is worst case chosen. Just the randomness of the sample says, let's look at the sample. What's the expected number of k-cliques? It's really proportional to, you have n vertices there, you have s vertices here, s over n to the power of k times the number of k-cliques in the mother graph. Exact expressions, more or less, you can calculate. What's the variance? Variance really kind of maybe a little harder to calculate, but one proxy for variance is this differences. How much can the number of k-cliques change by if I change one vertex in the sample? Okay. And how much can you change it by? Well, actually, this new vertex could be involved in a k-clique with everybody else in the sample. Okay, so suddenly I have s to the k minus 1 new cliques popping up because I changed one vertex. This is just too high. If this is the number that we have to work with, then actually s really has to be p to the k squared, and 1 over p to the k squared, and so we're not going to be beating the naive algorithm. But this is what we want to beat. Okay. So what should we do? Okay. How much does number of k-cliques change by in this worst case graph? And I have no idea what this graph is. If I suddenly, replace one vertex by another, okay, I've taken a sample of s vertices and I've just changed one vertex from one to the other. How many new k-cliques could I add by this process? Let's take an example graph. It's a clique on the left half of the vertices and an independent set on the right half. I take s minus 1 vertices from this side and one vertex from here. I now replace it by one vertex from here. I've just added s to the k minus 1 cliques. This huge change in the number of k-cliques by just changing one vertex, s to the k minus 1, has vastly increased the number of k-cliques in this particular sample. And if my function that I'm analyzing shows this kind of sensitivity to one variable changing, then the concentration results, once you sort of open them up and unpack them and do the calculations, will tell you that, look, you really need a large size sample graph. Okay. So where can we try to gain over this without being, without somehow improving concentration bounds, which I don't know how to do. So here's the intuition. Look, I mean, if this difference is really looking like s to the k minus 1, but what should it really look like, the maximum difference when I change one vertex? In GNP, this number will be really looking like s to the k minus 1 times p to the k minus 1 choose 2. I mean, in order for this transferred vertex to form a k clique with this set of k minus 1 vertices, these guys must be a k minus 1 clique to start with. So, this really shouldn't happen. So I should already be filtering things out and throwing them away because they're not looking like random graphs. Okay. And this is one of the sort of funnest part of working with these quality control problems. I think this thing that I've highlighted in green, you want to quality control for some parameter rho, okay, number of k cliques. You can pick any parameter you want, graph k colorability, Hamiltonicity, anything else you want to pick, and run a quality control for algorithm for that as a filter, saying, oh, any algorithm that fails this filter will be, any input that fails this filter will be rejected. What happens to soundness? I'm rejecting more graphs, all the better. What happens to completeness? I'm rejecting little of one fraction of the graphs. No problem. I can do this, it's completely safe. And this is, I think, what makes quality control a very nice definition. Just, exceptionally clean. You can just compose algorithms very, very nicely. It's very rare to see this kind of composability in property testing, sublinear algorithms, average case complexity, etc. This has that very nice property. Okay. So this is exactly what we're going to do. We're going to say, let's run a filter, which will say, if the number of 1 cliques is wrong, let's throw away this. The number of 2 cliques is wrong, throw it away. And the number of 3 cliques is wrong, throw it away. All the way up to k cliques. If any one of these numbers that are on the sample looks wrong, throw it away. And you still have pretty good flexibility room. You can accept all the remaining graphs, and hopefully now we're in better shape. So now the question is, how do we analyze this and prove this? Okay. So let me first tell you what the algorithm was, just in case you missed it. We're going to sample these S vertices independently with repetition from our set of size n. Look at the number of L cliques that there are in this induced in this new graph on these things. If the number of L cliques is not consistent with GNP, throw away this graph. And this, if this is true for any L between 1 and k, we throw it away. If not, we accept. The query complexity is good. It's S squared. And we will hopefully work with S equal to 1 over p to the theta of k. Okay. So this is going to be our target, and this is what we will eventually prove.
So the queries are all pairwise edges, all pairs.
Yeah. So once I've sampled these vertices, just for every pair, query them. And the running time is still s to the k, which means 1 over p to the theta of k squared. So we may be beating sublinear worst case algorithms in terms of query complexity, but not in terms of time complexity. They were also actually running, after they ran 1 over p to the k squared queries, they ran in that much time also. We're faster, fewer queries, but same time. We will improve the query complexity later, but for now, we'll be happy with this. Okay. So let's make a kind of a strong assumption. Suppose it was the case that no matter what sample of S vertices we chose, the number of k minus 1 cliques is really roughly like in GNP. Okay, then we are in business. So then we would just go pick up the book, open McDermott's concentration and equality, ask what do you say for this bounded difference? How many? So as soon as I know number of k minus 1 cliques is the right number, s to the k minus 1, L to the k minus p to the k minus 1, choose 2. Then I say, okay, give me what's your concentration theorem for this thing. It'll give me a great concentration theorem that will work when S is roughly 1 over p to the order of k. And says that you will actually have very good concentration on this random subgraph. you will get a very good estimate of how many cake leaks there are in the whole graph. Okay. The exact calculations are sort of over here, but it's, did I get this thing right? Yeah, okay, so there's, at the end, how many cake leaks are there in expectation on a cake thing, and then in k-1 thing, these two divide each other, and this is where you see, rather than a p to the k squared behavior, a p to the k behavior. These two, the ratio of these two is like p to the order of k. And that's sort of where we are, what brings us into business. So this is great, but, how am I going to test for this property? I cannot filter for this property, right? I mean, no test will tell me for every possible subset of sample that you choose of size S, you will have the following property. I can hope for this to happen on a significant fraction. If I know that the probability over random choice of x1 to xs that this condition holds is high, can we do something about it? So has anybody seen, by the way, how many people have seen McDermott's inequality before? There's a few hands open. Anybody seen a McDermott's inequality with high probability bounded differences?
Something like that.
You've seen that, right? Okay, great. So it's a beautiful tool. It's actually okay, by the way, I think the reference that we found was kind of recent, but it's only like a 24 reference. Could that be? I mean, 2024. Yeah.
There's a version by Martin, which is sort of like a restatement of tolerance inequality, which has expectations rather than
Expectation maxims. Okay.
Uh,
And then I see. Okay, so
I was wondering if that could be different.
okay, it could
That is
be
from the 90s.
from the 90s. Yeah. So we found some reference. I mean, Cassandra, the student who's the main primary author over here, has been amazing finding all the right facts. And the reference was somehow from something fairly recent. So yeah, it's a bit surprising, but maybe it is. It's a beautiful proof. It's like 2 pages long, given McDermott's, but it's a black box reduction, but it's really very pretty. Anyway, sorry. So I think I already talked about this. We can't really assume this is true for all things. We have to worry about what happens if this holds with high probability. And here's this McDermott's with high probability bounded differences. It's due to Combs from 2024, apparently, but maybe this is, I should go back and look at this thing. Maybe it's a survey which talks about this thing. So suppose you're told that the probability of some event that you want is some, you want something to happen, the probability it doesn't happen is like delta. How does it affect the concentration bound that you're trying to prove? Well, the concentration bound that you're trying to prove will have like whatever was the original error probability plus 2 delta. This is something that everybody can live with, okay? Not a problem at all. And then it turns out, but there's also this thing that it actually changes what it is that we were, looking at in the expectation. So previously we were saying, the expectation of some event was mu sub k. Well, that expectation could now, because if we are conditioning on certain classes of events, could suddenly become mu sub k minus delta. Now, mu sub k is this p to the k squared quantity. Okay. I'm going to subtract off a delta from it. I better make sure that my delta is less than p to the k squared. If I'm wanting to make sure that the probability of some events that I'm looking for is less than p to the k squared, well, I have to run this experiment 1 over p to the k squared times before I can get to that point. Okay? So this seems like really bad news, except, I mean, look, if I'm looking at n coins and I want to know is this bias 1/2 or not, and I see that the 75% of the coins came up heads, the probability, it's not like what's my confidence in in this thing? It's exponential in the number of times I toss the coin. I don't have to worry about it. So maybe there are better ways of getting bounds on this thing. In fact, it turns out if I just count the number of k cliques in G, k minus 1 cliques in G, if I have a good estimate of that count, I will be exponentially likely to be concentrated around it, provided the number of k minus 2 cliques are also small, which will be exponentially concentrated around the right number, provided the number of k minus 3 cliques are also right, and so on. So this is perfect for us. Just go up, verify all of these numbers are good. And now for each one of these things, you can just say there's an induction lemma saying if the previous number of k cliques was in the right range, when you sample less, the probability that you will see the wrong number of things is exponentially small in the number of samples that you draw. And that gives us a delta which is small enough. And then we're in business and we can work with it. So this basically pretty much concludes the thing, where there's this kind of a nice definition that we ran in, that we liked, that we proposed. We say that a graph is sort of exponentially quasi-random if, when you sample random vertices from these things, the number of k cliques that you see is roughly what you should see in GNP. And if the nice thing that we can say is that if your graph is exponentially quasi-random with respect to L cliques, then we will reject this graph if it is not exponentially quasi-random with respect to L plus 1 cliques with high probability. If you're exponentially quasi-random with respect to all cliques from numbers 1 to k, then you actually have the right k clique bound. We are happy, we take it. If you are not, then at one point you will jump from being quasi-random to not being quasi-random. At that point, our algorithm will just reject it. Okay. And the query complexities are, are very tame and work. Great. So this is the query complexity. How am I doing on time?
15 minutes.
Okay, sounds great. So, so the good news, yeah, we have better query complexity. The bad news is we do not beat the running time of the best known sublinear worst case algorithm, and we'll try to fix that in the next part of the talk. Okay, so I'll tell you very briefly. So the nice thing, I mean, you might hope to say, okay, look, you just sample the vertices, you have the graph in front of you, let's just find out how many k cliques it has. But even counting, if you don't go back to our assumptions of quality control, if you don't rely on the weak completeness condition over there, this is not going to work, because at the end, you will be asking questions like, is there a k clique in the graph? And fixed parameter tractability, etc., already tell you that to find a k clique in a graph, you really need to, in an n vertex graph, if you want to find a k clique, it'll take you n to the k time. S vertex graph, s to the k time. That'll be back to 1 over p to the k squared. Yes.
So you said you can reduce number of vertices from n to s to try to sample and find a k clique there. And you said the problem with this is variance. It's just too much in general to do. Why not also in that S you sampled S vertices? Don't try to find a k clique. Try to find a let's say a p clique, for example, or some not p, some let's say k2 clique, for example. K2 is another number where the expected number of cliques you'll find is proportional. Like in this S inductive graph is proportional to the number of cliques you'll find. Number of k cliques you'll find in the n vertices graph. In the original graph.
So essentially that's what we're doing, right? We're just looking for all numbers L from 1 to k. For each one, we are saying, okay, is the number of k cliques roughly right? And we are accepting or rejecting. Now, you could say, look, we'll stop at some earlier point and then just not do the rest of the computations. Then you would need to be able to prove that if you counted the number of 10 cliques and that's right, then maybe the number of 100 cliques is also going to be right. Okay, so I don't know if were you trying to improve the query complexity or the time complexity?
Yeah, I was going back on that. In the naive algorithm, the very naive algorithm, like over there, yeah, the variance issue kind of gets solved if you reduce the k you're trying to find k clique.
Right, the variance will reduce, but at the end, I mean, it will not end up. You really need to know whether the number of k cliques is right. The number of square root of k cliques might be correct, but the number of k cliques may be wrong. And then what do we do with it?
But you can choose that that k2 has such a number which is like on expectation you'll find the same number of cliques. Like just
Same number of cliques as
we
what
find
cliques?
same number of K2 cliques on a S vertex graph as the number of K cliques on an N vertex graph.
I don't think it's going to work, right? I mean, n is smaller. Okay, so maybe we'll take this offline, but this is not going to work, I think. N is larger than S, K2, probably you have to think about K2 larger than K then, otherwise, yeah, okay. All right, so some things, so in our case, for example, so going back to our thing, we have S vertices, we sample this. Our plan is not to change the algorithm completely, but just implement this last part better. Rather than counting the number of K cliques explicitly, do something else, which works as a proxy for that. And once again, we'll try to take advantage of the fact that we can reject we can reject from the right distribution graphs which have the right qualities with some positive probability, it's okay. And here actually we ended up using some work on quasi-randomness. This is the kind of work on, these are works that have been trying to propose deterministic definitions of what makes a graph random. And there's a beautiful series of works, and including, I think, in Yufei Zhao's latest book on, graphs and so on. I don't remember, random graphs or something. Sorry?
Random graphs are really common.
Random graphs and narrative combinatorics. Thanks. There's a lot of coverage of this material, and some of those tools turn out to be perfect for us. And let me tell you a little bit about that. One of the notions that's in that book, but also it goes back to 87 work of Thomason, is this notion of something called a jumbled graph. Now, a jumbled graph, if people haven't seen this expression before, let me know, but this has been the sort of a prototypical definition of what it means for a graph to look random. You look at any two subsets of vertices x and y, ask how many edges are going from x to y. Over here, it should be roughly the number of vertices in this set times the number of vertices in that set multiplied by p, with a difference which is roughly beta times square root of the two set sizes. This is what's the engine, this is what comes out of expander mixing lemma. If you have a graph which is a good spectral expander, it will satisfy this kind of a property. Random graphs have this property, etc., etc., etc. So in 87, Thomason defined this notion as if a graph satisfies this thing, it's called P beta jumbled, where P is roughly like this graph looks like a GNP, and beta is a parameter which says how close to GNP do you really look. And the nice thing about it is actually, GNP graphs are really very nicely jumbled. By the way, beta is not going to be a number less than 1. It's actually somewhere between 1 and square root of n, I think is maybe 1 and little o of n is like are all good numbers. Beta is going to be larger than 1, but you're not going to, you don't need it to be very little o of n is good. If a graph happens to be very close to being regular and also very close to being co-regular, you take any two vertices and ask how many common neighbors they have. That's roughly what you expect, p squared times n plus or minus epsilon. Then this graph is actually pretty nicely jumbled. Okay, you would expect this epsilon to be little o of 1. Right? 1 over square root of n is kind of good bounds for these things. And so this is going to be like n to the 3/4 jumbled, right? So 1 over square root of n and something. So little o of n jumbled. Okay, so that's pretty good. So random graphs are going to be jumbled.
And why is this better than that one?
Sorry.
There is n to the 1/4.
Yeah, random graphs are going to be n to the 1/4 jumbled. That's correct. But this is a look at this
statement with just regular and co-regular.
Yeah, every graph that's like this. So you could really prove that a random graph is n to the 3/4 jumbled this way.
Okay.
But on the other hand, it's kind of a little worried about it. Maybe it wasn't n to the 1/4, maybe n to the 1/2. But I don't know. But still, this is going to be weaker. But this is easy to test. I mean, I can just go look at this graph and count how many edges there are and how many co-edges there are, and that's it. So it's like an n to the 4 time algorithm, maybe, or n to the 3. Okay. And if the graph is sufficiently jumbled, like in particular p times p to the k times n, so that's the kind of little o of n behavior that you need, then actually for any graph of size h, the number of induced subgraphs of H that you will see is going to be similar to that in GNP. And that's also all of these kinds of results, I think, are due to Thomason. But if not, they've been proved subsequently between then and now. There's a paper by Conlon, Fox, and Zhao that we do cite in our paper. For many of the proofs, actually, Thomason's paper is kind of hard to retrieve. Okay, it's not available online, not even in the Russian archives. And so you really can't find the proofs from there. But many of these things you can actually recover from Zhao's book, which is available online. All right, so this immediately gives us an efficient algorithm, and it really has to go through this first, the McDermott type analysis to say, oh, you can reduce it to a small sample complexity. Now I have this 1 over p to the k sized graph. I don't count the number of k cliques in it. I just count the number of, effectively the number of edges and the number of 4 cycles, because you're counting for every pair of vertices how many edges, how many other vertices they have in common. That's roughly like a 4-cycle count. If these numbers are roughly like in GNP, then you're in good shape and you can just take it to the bank and the number of k cliques is going to be right. Okay. And so once again, there is this thing that, we're saying basically if the graph is not jumbled, we're going to reject. And if it is jumbled, then we're going to accept. And that turns out to be a pretty good proxy for counting the number of L cliques from 1 to k. Maybe we might actually do it for, count the number of k cliques for L equal to 1, 2, 3, 4, and then you can appeal to this thing. All right, so like I said, the results extend to counting the number of induced copies of any graph H that you want. The parameter that you get is exactly the maximum degree of this graph H, which is kind of unusual in the sense whenever you look at some of these concentration results, they'll say, oh, if you want to find out how many copies of some graph H are there in something, it's the arboricity of this graph or the degeneracy of this graph that matters. But in our case, it's actually provably the maximum degree that's the most important parameter. We also have an improved result. I mean, we have these big constants which are sitting in front of k in the exponents, and these constants are not tight between upper and lower bounds. They're off by constants like 10 or something, but not like k. So, but for triangle counting, we can actually get even better results. But here we just take off-the-shelf algorithms in sublinear algorithms literature and say that, look, if you put them together the right way, in particular over here, we'll say if the graph has the wrong arboricity, whatever that number parameter is, we'll reject it. And if it's not, then we'll use an algorithm which works well for low arboricity graphs and then apply it, etc., etc. That gives us the exact right bound, even including the exponent of p of theta tilde of 1 over p for triangle counting in graphs. Okay, so H counting lower bound was going to be on the board, but it's not. So conclusions, just it's a new class of problems, and I think it's really very clean class of definitions. Easy completeness condition, except most graphs. Easy soundness condition, just reject on the worst case, independent of the distribution, and somehow the asymmetry between the distribution appearing in completeness and not in the soundness makes it a more sound definition to work with. It's also very nicely composable, like we're saying in this things. And then there are a bunch of interesting non-trivial algorithms over here. Hopefully you'll see me all. Okay, thank you. Yeah, okay.
So in these problems, I mean, is there any use of being being adaptive in your queries at all?
Good. Yeah. I mean, so adjacency matrices typically tend to not be very helpful with respect to adaptive algorithms. That said, I mean, many of the actually the triangle counting algorithm that we have here is probably an adaptive algorithm. It does work in the adjacency list representation of graphs. Here it makes more sense. You can, when you're given an adjacency list of vertices, you can quickly compute its degree. You can, just guess the degree and keep doubling till you find the list has run out. And once you start hitting high degree vertices, maybe you do more explorations from there. Or if it's a low degree vertex, you do less explorations from there. So in that model, adaptive algorithms could be useful. And for all I know, our algorithm might be very adaptive in that case.
Was the assumption made on K being constant, or was it allowed depending on P or N?
K depending on P and N, there are various places, especially in the gap between upper bounds and lower bounds, there could be leading constants of the form 2 to the K squared in various places. So, by the way, here's a canonical. So, let me just say one thing about the lower bound, which says y is p to the delta of h necessary. How do we prove it? First, you want to say that, look, I want to create some graph which has lots and lots of copies, induced copies of some graph h. I don't know what h is. How do I create a graph which has lots of induced copies of h? Well, turns out you should just take the random graph with p equal to 1/2. If any graph has a lot of copies of h, this one will have at least 2 to the k squared smaller fraction of the same number of copies of h. Okay, so this is where we see factors that look like 2 to the k squared and so on sitting there. So we're definitely throwing them away. So if we brought out those constants explicitly, and it makes sense if p to the k is different than 2 to the k squared, then we might still have interesting results. I don't think there's any other place where we really suppress some very major dependence on K. It's just useful to think about it in that setting. Yeah. Oh, sorry, you didn't know.
I know. So this notion of jumbledness and there were these papers of Fan Chung and Ronald Graham.
Yes, yes.
So it's related to. So that was there were multiple definitions. You count the number of C4s. That's roughly what you would expect in a random graph. You look at the second eigenvalue, etc., and they are all equivalent to each other. This is roughly what it is.
It's the same literature. I think Thomason's came first, and then Chung and Graham and so on came later. Chung and Graham proposed many other definitions of quasi-randomness, some maybe a little bit more robust than jumbledness, etc. One thing we would have liked to see is some version of jumbledness which is not with a for all quantifier. Jumbledness is for every pair of vertices, blah, 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 something on. We were hoping initially to get a direct, thing which says when you sample something, some nice things happen with high probability. It was just not working out. And at that stage, we were looking at a lot of the other definitions. At the end, we were able to just go back to the oldest definition, probably in the literature on this field.
The second thing was, are there sort of natural algebraic settings where these questions might still have to say something more interesting than what we already know?
That's a good thing.
I mean, here this p to the k bound to me is a bit surprising. The fact that it works out, given the p to the k square.
Given the p to the k square. Yeah, I mean, actually, it's not an answer to your question. It's completely tangential, maybe, but somehow, I mean, the natural setting in algebra, we have seen this completeness and soundness being, jostled quite a bit in the literature, especially when we apply it in PCP type context. We suddenly say, oh, look, we would have liked to accept linear functions and reject things which are far from linear, but I'll actually not even accept all linear functions, but only those supported on a few variables, or maybe change the soundness condition. And then the quasi-randomness, only things that look very random must be rejected, etc., etc. So we've done a lot of perturbation in the property testing world, which are similar to this thing. So I don't know. I mean, maybe some of those results can be expressed in terms of, in the quality control language, it's doing something interesting.
But a more general interpretation of, what seemed like independent.
Yeah, you could say that, but also there's this thing. I think it's a very clean soundness condition. We are sort of more firm about soundness here than the completeness condition. Whereas very often things like long code testing will say you must accept long codes, and then the soundness condition is like a whole collection of different things depending on which paper you read. So here we are kind of firming up the soundness condition, and we're saying, oh, look, completeness can be different depending on which algorithm you run.
Other questions? Okay, if not, like.